All right, this is the video recording for Algebra 2, Unit 5, Lesson 5.5. All right, this one's going to talk about fully solving polynomial equations. And we do obviously have a lot of practice with this, but now we're going to work on doing this more broadly with all polynomials. All right, not just the linear and the quadratics that we've been working a lot with. All right, so again, reminding ourselves here that if you have a root, that means it's where x is going to be equal to 0. Okay, so if you have x minus a, that means that a is the root of the polynomial. Again, because if I have x minus a equals to 0, I can move a to the other side. All right, so clearly there we have 1, 0, or root. Again, knowing that this is the factor and this is the root, okay? And again, we do call roots also zeros. Okay, so we talked a lot about this earlier, but just reminding ourselves here that we can have up to the number of the highest exponent of roots. Okay, and I know that sounds a little confusing here, but we'll talk more about that. Okay, so again, we have this thing here where we can look at expressions and we can know based on maybe our constant, maybe that first polynomial term, right? We are able to calculate what those roots might be. And we did introduce ourselves to this in the last unit here, but we have the rational root theorem, right? So this is where if we write our function in our standard form, we have p as the factor of the constant term and q as the factor of the leading coefficient, right? And if we put all the factors of p over all the factors of q, that gets us all the possible rational roots that we can have. Okay, so in other words, if you divide those two out, all of those are potential or possible rational roots. Again, the reason they are possible is because we will limit them down to what's actually true here. All right, and remember though, if we can have 3 roots, right? So if our degree is our highest degree is 3, then that means we're going to have 3 roots. All right, and that includes real and imaginary roots. All right, that includes real and imaginary. Right, and imaginary are complex numbers, right? With the use of the letter I there. Again, I standing for the square root of -1. All right, so that would be our imaginary, and then again also our complex, right? So our non-whole number integers. All right, but focusing in here on listing all the possible rational zeros. All right, if we click on this here, consider the polynomial expressed there. All right, so before we do this, though, I want to point out one thing. So written in standard form, okay, we have the highest degree is x to the power of 4. All right, so that means we can have 4 roots, right? That means 4 roots, whether they're a combination of real and imaginary, or they're all real or they're all imaginary. Okay, that's up in the air. But we know that regardless, when we add them together, we have to have a total of 4. So if we use our factor theorem that we just talked about there, we all have all the factors of p and all the factors of q. So then we make all those different combinations here. So you're going to go 1 divided by 1, 1 divided by 2, 2 divided by 1, right? So we're going to write all those out, and then we simplify, right? So obviously if some of them are repeated, we're going to get rid of those. And again, if we can limit it down, and again, instead of writing 1 over 1, we could just write 1. So again, simplifying it down, and when we simplify, we're just left with this values, okay, with this values. All right, so it doesn't look too terribly awful, right? We have 1, 2, 3, 4, 5, 5 values, and we have plus or minus both of those values. So right now we have 10 potential factors. And obviously this was x to the 4th, so we know we're not going to have all 10 here. Okay. Again, another example here, 3x to the 4th, there's going to be 4 roots. We put all of plus or minus p over all of plus or minus q. We simplify, and we're left with, again, now a longer string of values here. And this is a perfect example of why we're going to continue talking, because we don't want to go through and test every single one of those options. So let's look at what we can do here, right? So using our rational root theorem, we have that list of roots, okay? And one of the things that it'll tell us here is that it cuts down on the amount of work here, right? It tells us the number of unique roots that we can have for a polynomial, all right? And again, unique roots being that they're not complex conjugates of each other, right? They're totally unique to each other. Now, again, I just mentioned this here, but there's a relationship between the degree of the polynomial and the number of roots. So x squared has 2 roots. Again, x squared has 2 roots here. All right. And this is one of our fundamental theories, our theorems of algebra. Okay, so again, it's just knowing that if I have x squared, it's going to give me 2 potential values for x that will both be incorrect. All right, x to the 4th, there's going to be 4 potential values. All right. Now, looking here, okay, hopefully this isn't too difficult. Again, you got to check that it's in standard form, but x to the 4th is going to match up with 4 roots. X to the 1st, 1, x squared. See, I rushed. I skipped out on the most important step there. It's not in standard form, right? See? 4x to the 5th, right? So that one would trip you up. That's x to the 5th is actually the degree of the polynomial and the number of roots that it's going to have. All right, I have 2x minus x to the 6th. So again, it's not written in standard form, but you should be able to match them up accordingly. All right, so just another example here. All right, we talked about this thing, but let's hone in on it. This thing called multiplicity. All right, and what multiplicity means is you're going to have 2 identical roots. So if we solve this one here, we're going to get x minus 5 and x minus 5. So instead of saying 5 twice, what we're going to do is we're going to use this concept called multiplicity. All right. And what we would do is we will change the way that we state our roots. Now, here it says x squared, okay, identifying obviously the 5, 0 is one of the roots there, okay? And we're not going to show 2 dots, right? We're not going to show 2 dots. And when you're looking at the intersection, again, it's only intersecting at one point, but it has this thing, again, called multiplicity. And another theory that will tell us that we have multiple roots at the same value is because of this thing of complex roots. All right, so again, not all roots are real numbers, and we can have complex numbers, we can have imaginary numbers, or some combination thereof. But we did talk about a theorem here, and let's walk through it quickly. So when I take the square root of negative 9, I get plus or minus 3 times by I, right? So plus or minus 3 times by I, because when I write negative 9, or the square root of negative 9, I can write that as the square root of 9 multiplied by the square root of negative 1, and we know that the square root of negative 1 is I. Okay, so when we look at that, though, again, remember, and I guess I should have backed that up there before I move forward. Okay, so it's plus or minus. Plus or minus. That means there's 2 roots there. Okay, and this is why we have that complex root theorem. We have to have 2 roots because we don't know if it's negative 3 squared or if it's 3 squared. Regardless, both of those answers would give us 9. All right, so we have to say plus or minus, and that's why when we have one complex root, we're going to have the opposite of that root, or the pair. A better way of saying that is the pair to that root. So if I had positive 3i, I would also have to know that negative 3i is a root. All right, there's 2 roots. Each one of them are imaginary. Now, what does that mean? It means nothing, except for the fact that except for the fact that it doesn't cross the x-axis. Remember, imaginary and complex numbers aren't actually on our graphs here. All right, so we'll still have our normal graphical shape, right? We can have our same shape. It doesn't affect anything like that. But when you have only imaginary or complex roots, they do not show up on your graph. All right. Also, if we look here at this one, okay, so we look here at this one, we find out we have -2 plus or minus I. All right, -2 plus or minus I. Okay, that's both of our complex roots here because we have x squared, so we can only have two potential roots, and it's going to be the positive version and the negative version of this. All right, again, -2 plus I and -2 minus I. But regardless, it doesn't cross the x-axis because the roots are complex and they're not shown on our graphs. All right, so reminding ourselves here, the conjugate radical theorem says it's a plus square root of b is a root, then a minus the square root of b is also a root, right? And again, the same thing is with the complex conjugate theorem, right? If I've got the positive version, I have to have the negative version. All right, so then looking at this, is if a polynomial has a degree of 3, it can have 3 total roots, right? It can have three total roots. But if we have a complex root, all right, if we have a complex root, we have to have factors of 2. So this could either be 2, 4, 6, whatever. But remember, because they're in a pair, if you have one, you have to have both. All right. So if we have 3 real roots, that means we can have 0 complex roots, right? Sorry, I think that the way that they're trying to say this is I can either have, if I have 1 real root, I can have 2 complex roots, okay? Because again, complex roots come in pairs. So I can either have 1 real root if I had 2 real roots, right? Since I can only have up to 3, this would be telling me that I have 1 complex root. So that's not plausible and that's not real. So what this is saying is I can either have 1 real root and 2 complex roots, because that's going to give me my combination of 3, or I know I have 3 real roots. Right? That's what this theorem is saying here. Okay, so then moving forward here with Descartes' rule of signs. All right, what this means here is that when we're looking at our rational roots there, right, our whole number integers, okay, we can either have positive or negative real roots, right? So when we're talking about roots, okay, we have the real or the imaginary. So when we have our list, right, we generate our list of our roots, those p's over q's. What's going to help us eliminate those down is this Descartes' rule of sign. Okay, so again, when we're talking about this, we have the number of positive roots is less than or equal to the number of sign changes for our normal polynomial. All right, and I know that this is kind of confusing, so let's come down here and look at this example. All right, so it's saying the number of positive roots is less than or equal to the number of sign changes for the terms of the polynomial function. Okay, so if I look here, I have a positive 4x cubed, and I have a negative 8x squared. All right, so this goes from positive to negative, so that's a sign change, right? And so what Descartes is saying is count up the number of sign change in the normal function, and this is going to tell you how many positive real roots you can have. So I go from positive to negative, that's 1 change. Negative to positive, that's 2 change, and then positive to positive. So I'm going to have 2 real roots, okay? Or less. So I'm going to have 2 or less real roots. Okay, again, because it's either less than or equal to the number of sign changes. All right. Then what happens here is we also look at the negative real root options, okay? And in order to calculate this, what we would do is we would plug in for f of negative x, right? So instead of x, we plug in our negative x, all right? And what you'll do then is you'll do the same process once you've simplified, right? You'll count the number of sign changes. And what that would tell you is how many you can have of negative real roots. All right. And then what this last rule here is saying is in each case, the number of real roots is less than the number of, if it is less than the number of sign changes, right? So that's saying here, this is x, this one is x cubed, okay? So this one was x cubed, and we found out that that means it's going to have 3 total roots, okay? Then we just found out, sorry, I erased it, this can have 2 or less real positive real roots, okay? So positive real roots. And what this is saying is once we calculate our positive real roots, if I have less than what this is telling me I should have 2. So if I have less than 2, right? If I have less than 2, then the number of roots has to differ by a multiple of 2. All right? And the reason that is because of that rule of complex conjugates, right? So if we had the positive of our complex, we'd have to have the negative, right? Those theorems we just went over. So what this is saying is if, okay, in this example, if I don't have 2, right? If I don't have 2, then I'm either going to have 2 or 0 positive real roots, right? Because if it's not real, that means it has to be imaginary. It has to be imaginary, right? And for an example, if we came up with, after we plugged in our negative x value, it said we could have 1 or less negative real roots, okay? Well, according to this, if I have less than this, I have to have a multiple of 2. I have to have a multiple of 2. So if I have less than 1, if I have 0, that's not a multiple of 2. So this one's telling you you're going to have 1 negative real root. You're going to have 1 real negative root. All right. If we have another example where we come up with 3 positive real roots, that means it can either have 3 or 1. Because if it doesn't have 3, then those other 2 have to come from one of our more complicated numbers, right? So we'll get to more examples with that. All right, so I'll let you guys do this one here. I'll quickly walk you through it, but it has 4 potential roots. All right, p's over q's, right? So you would do p's over q's and figure out how many total roots we have. So we have potentially 4 roots here. All right, so then what we can do now based on what we just learned is how many roots are positive. So we're going to look at how many times the sign changes. So if I look here, it goes from positive to negative to positive. All right, positive to negative to positive. So that's 2 sign changes. So according to Descartes' rule, we can have up to 2 positive roots. All right, and just like we said, since we can have 2, that means we either have 2 or none. Either have 2 or none positive real roots. Okay, then what you do for the next one is we have to plug in negative x to find the number of negative roots here. All right, and what you do is you square or cube or whatever to the power of the negative x sign, and then you simplify. All right, so it gave you here negative x cubed, right? Well, that would be negative x times negative x, which would give you a positive x squared, but then you have positive x squared multiplied by negative x, so that gives you your negative x cubed. All right, but something like x to the 4th, that's negative x times negative x times negative x times negative x, right? All those negative signs cancel, so this is still positive. So we then go back in and we count the number of sign changes. So this is still 2, so this is saying we either have 2 or 0 negative real roots. All right. Here's another example. All right, here's another example of one that we were talking about earlier. So here's an x cubed, right? Here's an x cubed. If it has 2 sign changes, it's either going to have 2 or 0 possible roots. All right, and in this one, it's going to have one negative real root. Okay, and what this is saying is you're going to have one negative real root. There's no or option, right? There's no or option because there's no option to have -1 number of real roots. All right. So then I know this is a long one here, so bear with me, but it's super important. Okay, we're almost closer to solving those higher degree polynomials. But first off, we have to talk about these things called upper and lower bounds. Okay, an upper bound is a number that says nothing will be greater than this number, right? It is a bound, so everything stays in between it. Upper means it's the highest number there. All right. So similarly, a lower bound is a number that is less than or equal to the number of all real roots. So what that's saying is no real root will be lower than that value. It could be that value, but it won't be any lower than that. All right. For a positive number, all right, f of x is divided by, if f of x is divided by x minus c, right? If it's divided by x minus c, then the resulting quotient and the remainder have no sign changes, okay? Then f of x has no real roots greater than c. All right, and I know that's a little bit confusing. So what that means here is it's referring to when we are doing our normal division problems. Okay, so if we were to carry this out either using long division or using that synthetic substitution method that we learned, if you run through and you plug in the value of c, okay, if you plug in the value of c for the synthetic division and all the values that come out are positive, then that would mean that that's the upper bound, okay? That's the upper bound. On the other side here, our lower bound, okay, it's still saying the same thing. So we plug in this new value of c into our synthetic division, all right? And this one's saying if it has alternating signs, okay, if the quotient and the remainder have alternating signs, right? Positive, negative, then there's nothing lower than that. All right, there's nothing lower than that. And yes, we'll work through a couple problems here. All right, but if there's no sign change in the bottom row, that means it's the upper bound, and any number larger, okay, any number larger than this can get deleted, right? And then on the other side, if you have your lower bound, okay, you have that negative, positive, alternating signs, you found your lower bound, okay, then that means there's nothing lower than that value. All right, so for example here, 2, negative 13, positive 36. So it's positive, negative, positive. Okay, we've got all these possible roots here. This is all the factors of p over all the factors of q, which is our 2 value. All the factors. Yikes, lots of them. Okay, so then what we're going to do is we're going to use Descartes' rule of sign, and it's going to say, hey, we're either having 2 or no rational roots. Okay, we have 2 or no rational positive roots. Okay, and then according to his other rule, right, when we plug in for negative x, there is only one possible negative real root. Okay, there's only one possible negative real root. So what we can do is we can figure out our upper or lower bounds to get rid of a lot of these options. Okay, so 9 is near the middle, so usually that's where we start. You pick a number that's right around the middle, okay, and you can develop your own technique if you want, but that's the technique that I'm going to be using here. Okay, pick a number right in the middle, okay, and then try to figure out if it's a root or if it's one of your upper or lower bounds here. Oh, apologies. Somehow that skipped really far. All right, so then what we do here is we plug in 9 using our synthetic division method. So I carry down my 2, my negative 13, and a 0, because remember, we have to write this in standard form, so we don't just go from x squared to our constant. So we have a 0 here for our x to the power of 1 term, and then we add our 36. Okay, we do our synthetic division, we get a remainder that is positive, right? We get a remainder that is positive. So this is not a factor, right? It's definitely not a factor. And 9, positive 9 is an upper bound, right? It's an upper bound because no value higher than this, right? No value higher than this is going to be a root, since all of these values are positive or have the same sign, right? Now, again, you can do whatever process, but the technique that we teach is splitting in half again, right? So out of our possible real roots, we've gotten rid of 9, 18, and 36, right? So we know it's between 1/2 and 6. Okay, so you try to split the difference again. So pick a number in the middle. I picked 3, right? Or they picked 3 as well. Okay, so then you run through and you do your synthetic division. All right, so this one has a remainder. Okay, so that means that it is not a real root. Okay, and it has a sign change. It has a sign change, right? It goes from positive to negative. So, and it's not alternating, right? It's just one. Therefore, we have not found a lower bound. Okay, we haven't found a lower bound. So, still, it can be anywhere from basically 9 to 3, and then anywhere lower than 3 there. Okay, so trying 6 here. Okay, we try 6, and it gives us a remainder of 0. So since there's a remainder of 0, that means it's a root. Okay, so we can pull out our value of 6 there. Okay, and then that gets us to a quadratic that we're really comfortable with factoring, hopefully by this point. So then we can just factor based on what we have there. And we get our values for our roots out. Okay, and I do want to point out, notice, okay, so when we would solve these, again, this would be x is equal to positive 2. All right, positive 2. And this would be equal to our negative 3/2. All right. And we didn't have to use the quadratic formula because we knew that positive 6 was a root, and based on this, that means we either had to have 0 positive real roots or 2 positive real roots. So that means I for sure knew that I had to have at least one more, which means that I could do my normal factoring process. All right. So the steps for solving a polynomial equation are right there. All right, I'll let you look at that. But it's basically the steps that we've been walking through here. All right, now understanding the whole list is kind of a lot here. So we'll go through maybe one example here. So, finding the roots for this one. Okay, it's x cubed. So I know that we're gonna have a potential of three roots. Okay, there's 3 roots there. Okay, so then the next step is to list all the rational roots using that theorem. So plus or minus p over plus or minus q. All right, so 36 has a lot of potential options. All right, but thankfully we're only dividing by 1 there. All right, so all of our possible rational real roots are right there. Okay, so the next we're going to use Descartes' rule of signs. Okay, Descartes' rule of signs. So looking at this, we go from positive, negative, positive, negative. So that's 4 sign changes. All right, so it can either be 4 or less real roots. 4 or less real roots. Okay, and since we know that there's only 3 potential roots, okay, that takes 4 out of the equation. That takes 4 out of the equation. All right, so we can look at that. All right. Then all right, so then when we're looking at our negative roots here, okay, we're looking at our negative roots here, it's telling us that we plug in for negative x, right? We carry that through. There are no sign changes though, all right? It's negative throughout the entire thing, so there's no negative real roots, okay? So since there's no negative real roots, we know that out of our rational list here, it's only the positive versions. So we can get rid of that plus or minus. All right, so now we have our possible list here. Okay, we can either try to go to find an upper bound, a lower bound. You can try to look somewhere in the middle, right? And again, that's kind of the technique that I go with, is go right in the middle, try to cut them in half. So testing 6 here, we use synthetic division. All right, and we end up with all positive values and a remainder. So it's not a factor, okay? But that means that that is an upper bound. So we don't have to look any farther than positive 6 there. So we're left with 1, 2, 3, and 4. All right. So we can test another one again, and again, it's whatever technique you want. I would have suggested testing somewhere in the middle, like testing 2 or 3, but they tested the upper bound 4 here to see if they could keep going down and down. All right, so once they did that, though, they were able to figure out, oh yeah, 4 is actually a root here, okay, and they know it's a root because the remainder is 0. then we pull that out, right? So we pull out our x minus 4, and we get this x squared plus 9. All right. And for this one here, when we are left with a quadratic, we can use any of the factoring processes that we learned here. Okay. Quadratic formula, or factoring, or completing the square. So for this one here, we don't actually need to keep with this, because what we can do is just move 9 to the other side, and we can take the square root of it. All right. And since we get this negative 9, that's going to give us our I value. This is going to turn this into an imaginary number. So when we take our answer, we get plus or minus 3i. Okay, so those are our 3 roots. And again, we just double check x cubed. So I should have 3. I have 3 roots. There we go. All right. I'll let you guys watch this video on your own here for more examples of how to do this process. All right. Same thing here. Go through and try to answer these multiple choice questions. Now, when we're looking at this, okay, we talked about graphing polynomials. All right, so we're going to look at some things with our graphs here. So what does the graph of this look like? It's x to the 4th. All right, and by doing our processes here, we can figure out our roots. Okay, so we know that that's where it's going to cross the x-axis. All right, and we also know a couple other things. We know that this is a positive 1 out in front. So the left and the right hand sides, the ending behavior is going to be the same, right? And we also know that this is the positive number 1 is going to tell us that our right hand side is going to end in the positive direction, that positive infinity. All right, and since it's x to the 4th, since it's an even number, that means it's going to have the same behavior. All right. And other things, again, plugging in values for y. All right, we can plug in values, get a couple key points there, right? Get a couple key points, and be able to kind of guesstimate from there. All right, so again, knowing that it's going to end in the same direction, both going up, and we know we have to cross that 4 times. All right, so find a polynomial with those 3 roots. Okay, so if it's got 3 roots, okay, then that means the degree has to be 3. All right, and we also know that this means that they have to all be set equal to 0, right? So what we can do then is multiply these out, right? So there we go. That would be an example of a function. All right. So then here, moving forward, just to confirm, the fundamental theory of algebra says that we can only have up to n number of roots, right? So if it's x cubed, you can have up to 3 roots. All right, what are the steps for solving a higher degree polynomial? All right, we walked through those quite a lot, but use our fundamental theory to identify the number of roots, use the rational roots theorem to create your list, use Descartes' rule to lower down that list, then we plug in synthetic division to try to find our bounds or our roots, right? That's the ultimate goal, is to find at least one root. Again, if we can get it down to something like a quadratic that we know how to factor, we can then use any of our methods for factoring further. All right, and then again, confirming that our roots are real by plugging them back into the equation and solving for 0 is always a helpful thing. All right, I will let you guys do this practice on your own. And then we can answer some of these questions here quickly. The complex conjugate. Okay, the complex conjugate theorem states that if I have a plus bi, then that also means a minus bi has to be a root. All right, looking at this guy, how many possible roots does it have, and how many negative roots? All right, so looking at this, I can have up to 4 roots. Okay, I can have four roots total. Okay, so looking here, I've got to use Descartes' rule of signs. So I'm going to go positive, negative, negative, negative. So I have 1 sign change, 2 sign change, 3 sign changes. Okay, so we can have up to 3 positive real roots or 1 negative real root, again, based on this theorem up here. Okay, and then if I were to plug in negative x, right, if I were to plug in negative x, it would have told me that I have one sign change, so one negative real root. All right, what is the upper bound for this value? Okay, and this would have to be, this would have to be tested, okay? This would have to be a tested one, but you can look here and see, well, negative 8's a low value, 1's a low value, and 2's a low value. All right, so you would immediately think 4, right? But then this would have to be where you actually go and you plug in for your values here, and you'd have to actually go through the process of the synthetic division and figure out which one of these, when plugged into our synthetic division, is going to have all positive values with no sign changes at the bottom there. All right, and then figuring out the roots for this guy. Okay, figuring out the roots for this guy. So first off here, you have x cubed. All right, so that means you can only have up to 3 roots. Okay, you can only have up to 3 roots. So this first one's knocked out there. All right, looking at Descartes' rule of signs. Positive, negative, that's 1 sign change. 2 sign changes, 3 sign changes. Okay, so we can have either 3 real roots or 1 real root. All right. And then what it looks like here is all 3 of these have 1 in common. So what I would do is test 1, make sure, confirm that that's a root, right? And then factor that guy out. Once we factor out x minus 1 from this entire thing, you can then see, is it going to be 1 plus my complex value, or is it going to be just 3i by itself? Okay, so again, plugging those in and double checking there. All right, so looking at the study guide then here. Okay, so we're looking for P over Q, right, where P is a factor of the constant and Q is the leading coefficient. So then again, listing those all out, simplifying, getting rid of duplicates, all of that nature. All right, so then this is saying, again, look at the highest value. As long as it's in standard order, it's going to be that leading term. All right, then knowing that we can have n number of unique roots based on the degree n, but if you have one complex, the positive version, you have to have the negative version, right? Same thing with imaginary numbers. All right, then using Descartes' rule of signs, counting positive, negative for the forward reaction is going to give you the number of possible positive roots, and then doing the negative x value is going to give you the number of negative real roots. Okay, then talking about here, upper and lower bounds. All right, so talking about our upper and lower bounds. All right, and then really figuring out how to solve. Again, understanding this process is going to be super, super helpful. All right, so again, when we do the process here, if you get something like this that's all positive, there is a remainder. It's telling you that this is an upper bound. All right, doing it again when you get 0, that's a real root. Okay, and if it's something small, again, something small like our quadratics, we know how to factor, right? That's your goal. Get it to a quadratic, and then you can solve it from there. So if you had x to the 4th, you might have to go through this process twice to find another factor, but we usually try to stick to the lower numbers there.